When choosing measurement hardware, one of the first specs people notice is resolution. You'll see terms like 12-bit, 16-bit, or 24-bit, and it's easy to assume that more bits automatically means better measurements. But here's the catch. Resolution is not the same thing as accuracy. In real-world test systems, accuracy depends on the entire measurement chain, not just the analog to digital converter. Resolution tells you how finely a device can divide a measurement range. For example, a 16-bit device divides its selected range into thousands of tiny steps, while a 24-bit device divides that range into even smaller steps. That can be useful, especially when you need to see small changes in a signal. But accuracy answers a different question. How close is the measurement to the true value? A system can have high resolution and still be inaccurate if noise, calibration drift, poor input range selection, incorrect signal conditioning, temperature changes, or grounding problems are affecting the signal. One of the biggest real-world factors is noise. Electrical noise can come from motors, power supplies, switching electronics, fluorescent lighting, nearby cables, or even the measurement device itself. If the signal you care about is small, that noise can bury the real measurement or make the reading fluctuate. In that case, higher resolution may simply give you a more detailed view of a noisy signal. That's why low-noise hardware design, proper shielding, filtering, and cable routing are so important. The goal is not just to collect more digits. The goal is to collect meaningful data. Another key factor is calibration. Over time, electronic components naturally drift. Temperature changes, aging components, regular use, and environmental conditions can all affect how closely a device measures against a known reference. Calibration compares your instrument to a trusted standard and verifies whether it is still measuring within specification. Without proper calibration, your readings might appear stable and repeatable, but they could still be consistently wrong. This is especially important in aerospace, defense, manufacturing, research, and quality control environments where traceability and confidence in the measurement are critical. Input range also plays a major role in real-world accuracy. Many DAC devices and instruments allow you to select ranges such as positive negative 10 volts, positive negative 5 volts, positive negative 1 volt, or even smaller ranges depending on the device. Choosing the right range helps the instrument use its available resolution more effectively. For example, if you are measuring a 100 millivolt signal on a positive negative 10 volt range, you are spreading the device's resolution across a much wider range than necessary. You may still get a measurement, but you are not taking full advantage of the hardware. When you choose the smallest range that safely contains your signal, you improve measurement detail and often improve practical accuracy. Then there is signal conditioning. Many sensors do not produce signals that are ready to measure directly. Thermocouples, RTDs, strain gauges, accelerometers, microphones, and bridge sensors often require some form of conditioning before the data is useful. This may include excitation, amplification, filtering, isolation, cold junction compensation, or linearization. This is why measurement-specific modules are so useful in platforms like Compact DAC, Compact Rio, and PXI. The right module does more than capture a signal. It prepares that signal for accurate measurement. Temperature drift is another hidden source of error. Electronic components can behave differently as temperature changes. A device that measures accurately in a controlled lab may perform differently in a hot factory, a cold outdoor enclosure, or a system that runs continuously for long periods. Datasheets often include temperature drift or temperature coefficient specifications, which describe how much the measurement may change as the operating temperature changes. If your system will be used in a harsh or changing environment, don't only look at the best-case accuracy spec. Look at how the device performs across the full operating temperature range. Grounding can also make or break a measurement. Improper grounding can introduce offsets, instability, and unwanted noise. One common issue is a ground loop, which happens when 2 points that should be at the same electrical potential actually have a small voltage difference between them. That unwanted voltage can show up in your measurement, making the signal appear noisy or inaccurate. Using differential inputs, proper shielding, isolated modules, and thoughtful cable routing can help reduce these problems. In many real-world systems, wiring and grounding practices are just as important as the hardware specifications. So, when evaluating measurement hardware, resolution is only one piece of the puzzle. It's about building a system where every part of the signal path supports trustworthy data. When noise is controlled, calibration is current, input ranges are selected correctly, signal conditioning is appropriate, temperature effects are understood, and grounding is handled properly, your measurements become more than precise. They become reliable. This concludes today's video. Thanks for watching. If you're looking for legacy NI parts, calibration services, or more technical resources, head on over to apexwaves.com to get what you need. Fast. We have thousands of NI parts in stock and ready to ship, including legacy and obsolete modules you won't find anywhere else. And if you found this helpful, don't forget to like this video and subscribe to our channel for more product highlights, how-tos, and industry insights.